Multi-leaders replication. So far, in this chapter we have only considered replication architectures using a single leader. Although that is a common approach, there are interesting alternatives. Leader-based replications has one major downside. There is only one leader and all writes will go through it. If you can't connect to the leader for any reason, for example due to a network interruption between you and the leader, you can write to the database. A natural extension of the leader-based replication model is to allow more than one node to accept writes. Replication still happens in the same way. Each node that processor write moves forward the data chains to all the other nodes. We call this a multi-leader configuration, also known as master or active-active replication. In this setup, each leader simultaneously acts as follower to the other leaders. Use case for multi-leader replication. It rarely makes sense to use a multi-leader setup with a single data center because the benefits rarely outweigh the added complexity. However, there are some situations in which this configuration is reasonable. Multi-data centers operations. Imagine you have a database with replica in several different data centers. Perhaps that you can tolerate failure or an entire data center, or perhaps in order to be closer to your user. With a normal leader-based replication setup, the leader has to be in one of the data centers, and all writes must go through the data center. In a multi-leader configuration, you can have a leader in each data center. Figure 5.6 shows what this architecture might look like. Within each data center, regular leader followers replication is used. Between data centers, each data center leader replicates its change to the leader in other data centers. Let's compare how the single leader and multi-leader configuration fare in a multi-data center deployment. Performance. In a single leader configuration, every write must go over the internet to the data center with the leader. This can add significant latency to writes and may contravene the purpose of having multiple data centers in the first place. In a multi-leader configuration, every write can go processed in the local data center and it replicated asynchronously to the other data center. Thus, the inter-data center network delay is hidden from users, which means the perceived performance may be better. Tolerance of data center outages. In a single leader configuration, if the data center with the leader fails, failover can promote a follower in another data center to be leader. In a multi-leader configuration, each data center can continue operating independently of the others, and replication catches up with the failed data center come back online. Tolerance of network problems. Traffic between data centers usually goes over the public internet, which may be less reliable than the local network which is within a data center. A single leader configuration is very sensitive to problems in this inter-data center link because writes are made synchronously over this link. A multi-leader configuration with asynchronous replication can use tolerant network problem better, or temporary network interruption does not prevent writes being processed. Some databases support multi-leader configuration by default, but it's also often implemented with external tools such as Stone replication for MySQL, BDR for PostgreSQL, and Golden Gate for Oracle. Although multi-leader replication has advantages, it also has a big downside. The same data may be concurrently modified in two different data centers, and those write conflicts must be resolved, indicated as a conflict resolution. We will discuss this issue in handling write conflict on page 171. As multi-leader replication is a somewhat retrofitted feature in many databases, there are often subject configuration pitfalls and surprising interaction with other database features. For example, auto-incrementing keys, triggers, and integrity constraints can be problematic. For this reason, multi-leader replication is often considered dangerous territory that should be avoided if possible. Clear with offline operations. Another situation in which multi-leader replication is appropriate if you have an application that needs to continue to work while it is disconnected from the internet. For example, consider the calendar app on your mobile phone, your laptop, or other devices. You need to be able to see your meeting, make read requests, and enter new meetings, make write requests. At any time, regardless of whether your device currently has an internet connection, if you make any change While you are offline, they need to be synced with a server and your other devices with the device is next online. In this case, every device has a local database that acts as a leader. It accepts write requests, and there is an asynchronous multi-leader replication process. Between the replicas of your calendar and all your devices, the replication lag may be hours or even days, depending on when you have internet access available. From an architecture point of view, this setup is essential, same as the multi-leader replication between data centers. Taken to the extreme, each device is a data center, and the network connection between them is extremely unreliable. As the rich history of broken calendar sync implementation demonstrates, multi-leader replications is a tricky thing to get right. There are tools that aim to make this kind of multi-leader configuration easier. For example, CouchDB is designed for this mode of operation. Collaborative editing. Real-time collaborative editing application allows several people to edit a document simultaneously. For example, Etherpad and Google Docs allow multiple people to concurrently edit a text document or a spreadsheet. The algorithm is briefly discussed in Automatic Conflict Resolution on page 174. We don't usually think of collaborative editing as a database application problem, but it has a lot in common with the previously mentioned offline editing use case. When one user edits a document, the changes are instantly applied to the local replica, state of the document on their web browser or client application, and asynchronously replicated to the server and any other user who are editing the same document. If you want to guarantee that there will be no editing conflict, the application must obtain a log on the document before a user can edit it. If another user wants to edit the same document, they first have to wait until the first user has committed the change and released the log. This collaboration model is equivalent to single leader replication with transactions on the leader. However, for faster collaboration, you may want to make the unit for change very small and avoid the locking. This approach allows multiple users to edit simultaneously, but it also brings all the challenges of multi-leader replications, including requiring conflict resolutions. Handling write conflicts. The biggest problem with multi-leader replication is that write conflict can occur, which means that conflict resolution is required. For example, consider a wiki page that is simultaneously being edited by two users, as shown in figure 5.7. User 1 changed the title of the page from A to B, and user 2 changed the title from A to C. At the same time, each user changes successfully applied to the local leader. However, when the changes are asynchronously replicated, a conflict is detected. This problem does not occur in a single leader database. Synchronous versus asynchronous conflict detection. In a single leader database, the second writer will either block and wait for the first write to complete or abort the second write transaction, forcing the user to retry the write. On the other hand, in a multi-leader setup, both writes are successful and the conflict is only detected asynchronously at some later point in time. At that time, it may be too late to ask the user to resolve the conflict. In principle, you could make the conflict detection synchronous. Wait for this write to be replicated to all replicas before telling the user that the write was successful. However, by doing so, you will lose the main advantage of multi-layer replications, allowing each replica to accept writes independently. If you want synchronous conflict detection, you might as well just use single-leader replication. Conflict avoidance. The simplest strategy for dealing with conflict is to avoid them. If the application can ensure that all writes for a particular record go through the same leader, then conflicts can occur. Since many implementations of multi-leader replication handle conflict quite poorly, avoiding conflict is a frequently recommended approach. For example, in an application where a user can edit their own data, you can ensure that requests from a particular user are always routed to the same data center and use the leader in the data center for reading and writing. Different users may have different homes, data centers. Perhaps Pick based on geographic proximity to the user, but from any one user point of view, the configuration is essentially single leader. However, sometimes you might want to change the designated leader for a record, perhaps because one data center has failed and you need to reroute traffic to another data center, or perhaps because user has moved to a different location and it's shown now closer to a different data center. In this situation, conflict avoidance breaks down and you have to deal with the possibility of concurrent write on different leaders. Converging toward a consistent state. A single leader database applies write in a sequence order. If there are several updates to the same field, the last write determines the final value of the field. In a multi-leader configuration, there is no defined order of write, so it's not clear that the final value will be in figure 5.7. A leader 1 be titling the first update to B and then to C. A leader 2, it is first updated to C and then to B. Neither order is more correct than the other. If each replica simply apply writes in the order that it saw the write, the database will end up in an inconsistent state. The final value will be C at leader 1 and B at leader 2. That is not acceptable. Every replication skip must ensure that the data is eventually the same in all replicas. Thus, the database must resolve the conflict in a convergent way, which means that all replicas must arrive at the same final value when all changes have been replicated. There are various ways to achieve convergent conflict resolutions. Give each write a unique ID, timestamp, long random number, or hash at the key and value. Pick the writes with the high ID and the winners and throw away the other writes. If a timestamp is used, this technique is known as last write wins, LOE. Although this approach is popular, it is dangerous, prone to data loss. We will discuss LWW on WW in more LWW in more details at the end of this chapter, detecting concurrent writes, on page 184. Give each replica a unique ID and let writes that originated at a high number of replica always take precedence over writes that originate at lower number of replica. This approach also implies data loss. Somehow merge the value together, order them alphabetically and then concatenated them. In figure 5.7, the merged title might be something like B/C. Record the conflict in an explicit data structure that preserves all information and writes replication. Applications code that resolve the conflict at some later time, perhaps by prompting the user. Custom conflict resolution logic. As the most appropriate way of resolving a conflict may depend on the application, most multi-leader replication tool let you write conflict resolution logic using application code. That code may be executed on write it or on read it. On write, as soon as the database system detects the conflict in the log or the replica changes of the conflict handler. For example, Bucardo allows you to write a snippet of Perl for this purpose. This handler typically cannot prompt the user. It runs in a background process and it must execute quickly. On read, when a conflict is detected, all the conflicting writes are stored. The next time the data is read, these multiple branches of the data are returned to the application. Application may prompt the user or automatically resolve the conflict and write the result back to the database. CouchDB works this way, for example. Note that conflict resolution usually applies at the level of any individual row or document, not for entire transactions. Thus, if you have a transaction that atomically makes several different writes, see chapter 7, each write is still considered separately for the purpose of conflict resolution. Automatic conflict resolution. Conflict resolution rules can quickly become complicated, and custom code can be error-prone. Amazon is a frequently cited example of surprising effect due to a conflict resolution handle. For some time, the conflict resolution logic on the shopping cart will preserve items added to the cart, but no item removed from the cart. Thus, customers will sometimes see items reappearing on their cart even though they had previously been removed. There has been some interesting research into automatically resolving conflict caused by concurrent data modification. A few lines of research are worth mentioning. Conflict-free replicated data types, CRDT. are a family of data structure for set, map, order, list, counters, etc. that can concurrently edited by multiple users and which automatically resolve conflict in sensible way. Some CRDT have been implemented in React 2 and 2.0. Regular persistent data structure. Track historical explicitly, similarly to the Git version control system, and use a three-way merge function, where CRDT used two-way merge. Operational transformation is the conflict resolution algorithm behind collaborative editing applications such as Etherpad and Google Docs. It was designed particularly for concurrent editing on an ordered list of items, such as lists of characters that constitute a text document. Implementation of all these algorithms in databases are still young, but it's likely that they will be integrated into more replicated data systems in the future. Automatic conflict resolution will make multi-leader data synchronization much simpler for applications to deal with. What is a conflict? Some kind of conflicts are obvious. In the example figure 5.7, two writes concurrently modify the same field in the record, setting into the two different values. There is little doubt that this is a conflict. Other kind of conflict can be more subject to the text. For example, consider a meeting room booking system. It tracks which room is booked, which group of people at which time. This application needs to ensure that each room is only booked by one group of people at any one time. There must be not be any overlapping bookings for the same room. In this case, a conflict may arise if two different bookings are created on the same room at the same time. Even if the application checks availability before allowing a user to make a booking, there can be a conflict if two bookings are made on two different leaders. There is not a quite ready-made answer, but in the following chapter we will trace a path toward a good understanding of this problem. We will see some more examples of conflict in chapter 7 and in chapter 12. We will discuss scalable approaches for detecting and solving conflict in a replicated data system.